So now that we've talked about in previous lectures phase transformations, we want to extend that discussion to talk about how do we actually go about thermally processing metals. Today we're going to talk specifically about annealing processes. And all annealing is raising a metal to an elevated temperature, holding, or sometimes call that soaking at that temperature, and then cooling slowly. So there's no sort of quenching involved. We're just slow cooling it all. So there are 5 types of annealing that I want you to be familiar with for this class, 2 of which are relevant to all metals, and 3 of which are relevant only to ferrous alloys. So the first is stress relief. The second is process annealing. Those 2 are going to be relevant to all metals. The 3 that are specific to ferrous alloys are spheroidizing, full anneal, and normalizing. So we're going to talk about each of these 5 to try to give you a flavor for each one. So the first one we want to talk about is stress relief. And the main idea of stress relief is that we're annealing to relieve some sort of internal stresses that have built up during however we've processed the metal. So I typically think of this as thermal stresses that might occur because of thermal gradients during cooling, but it could also happen from plastic deformation or phase transformation. So the feature here is that you're typically trying to do this at a low temperature so that cold work and other heat treatments that you've done to the metal are not affected. So this shouldn't change your ultimate strength or anything like that of your metal, but it should relieve some of the stresses that are internal. Okay, so if we're plotting that on a temperature time curve, stress relief, let me show you. I'm defining this purple dashed line as a transformation temperature of whether it's a eutectoid transformation or whether it's some sort of eutectic line, whatever the transformation temperature is for that composition and material. Stress relief is going to be a relatively low rise in stress, or sorry, low rise in temperature rather, hold and then let it cool down slowly. So usually like an air cool. Okay, uh, the next is that we'll talk about is a process anneal, and that's a little bit higher temperature than stress relief, and the goal is to actually negate some of the effects of cold work. So it induces what's called recrystallization, which is where high dislocation density areas in the metal will coalesce to basically form a new grain that relieves that high dislocation density area. And it softens the metal and increases the ductility. It still occurs below the transformation temperature. So if we're plotting what a process anneal might look like on a temperature time plot, you're going to raise the temperature to some level higher than the stress relief temperature, but lower than the transformation temperature. You're going to hold for some time, and then you're going to slow cool it in air. The feature here is that even though recrystallization is allowed, that's these high dislocation density grains can reform to low dislocation density grains. We don't allow any grain growth during this process. Okay. As we move to talk about the annealing of ferrous alloys, we need to introduce some definitions. The first is what's called the lower critical temperature. So let's look at this phase diagram that I'm showing you below. This is the weight composition carbon. There's your temperature. There's the 727 degrees that represents the eutectoid transformation temperature, and there's our eutectoid composition. So in this region, we have alpha and cementite. In this region up here, we have all austenite. Here we have austenite and cementite, and here we have austenite and ferrite. Okay, so this lower critical temperature, this is basically the eutectoid temperature, is the temperature below which any austenite that existed has transformed into ferrite and cementite. And so that's there. It's located just at that line. We call it A1. The next is the upper critical temperature, and it's the temperature above which only austenite exists. And from this plot, we can see that that's going to be for a hypoeutectoid alloy, it's going to be A3. And for a hypereutectoid alloy, so that's on this side of the eutectoid composition, then it's going to be what we call A sub Cm. So those would represent the upper critical limits. Okay, so those are our definitions. We now are going to go ahead and move to talk about the three types of annealing for ferrous alloys. The first one I want to talk about is what's called normalizing. Normalizing is done to refine grains that are elongated from a rolling operation. And I'm showing you the rolling operation here in this video as what you can see is this, you have the thicker piece of steel being squeezed in between these rollers to make sheets. And what that does is it makes the grains sort of long and thin. And the normalizing process is one that takes those long, thin grains, creates smaller, more uniform grains, and as a result of these smaller grains, it typically increases the strength. The way we accomplish this is that we heat to at least 55 degrees C above the critical limit and try to completely transform it to austenite. When we do that, that's a process called austenitization, or we're austenitizing the steel, which is just converting it fully to austenite, and then we cool it in air. And so that region of the curve is shown here on the phase diagram, uh, and so it's the highest sort of temperature with respect to all the annealing operations that we're going to talk about. Okay, the full anneal is going to be used to create coarse perlite in low and medium carbon steels. That's just the low or medium carbon is the carbon content. Any of those that are going to be heavily plastically deformed during processing. And the reason is that the coarse perlite, of course, is going to be uh, more ductile than like a fine perlite or a bainite is going to be, and so sometimes we want to create that microstructure so that the processing can happen without damaging our tools. And so we do this by heating it about 50 degrees above for either A3 on the hypoeutectoid or A1 on the hypereutectoid side, and then we hold it and then we furnace cool it. So the furnace cool is a little bit important because furnace cool means that it's going to cool more slowly than an air cool because we can control that temperature on the way down. And so the region that occurs in is shown here in blue. The last annealing process that we want to be familiar with is what's called spheroidizing, and we've talked about it before. It's just heating perlite to form spheroidite, and remember, the driving force for that is a reduction in surface area between the cementite and the alpha ferrite. The reason that we do it is because spheroidite typically is softer even than coarse perlite, and so sometimes it's not sufficient to go to a full anneal and create coarse perlite. We need to actually create spheroidite so that it's soft enough to do the machining that we want to do. And we do this by just basically heating to just below the eutectoid temperature and holding it to allow the formation of these cementite particles to form out of the cementite layers. So, and I think your book covers a few other methods that you could use for spheroidizing, but I'm just going to focus on this one. So those are all the annealing processes. Let me give you just a quick summary of what how these processes might look. So these are not to scale or anything like that, just to give you a feel for where they are aligned relative to one another. So I've already shown you a plot kind of showing you the stress relief diagram as well as the process anneal. So then, and this is now going to go up in temperature. So the next step up in temperature would be spheroidizing, and that goes to just below the eutectoid transformation temperature. Remember, to form those ferrite particles in the alpha or in the alpha ferrite matrix. Then there's a full anneal, and that's above the eutectoid transformation temperature. So the feature here is it is above that, but it also, look at the slope, right? It's a slower cool down, which means that's indicative of the furnace cool as opposed to an air cool. And then finally, there's the normalizing, which raises to an even higher temperature. And the point of that, right, is to make the grain sizes normal from these elongated grains that occurred during rolling, and then that's air cooled. So we have this cooling curve that's similar to the others except the full anneal. So that's kind of the summary of the annealing types that you need to be aware of. And then we'll move now to talk a little bit about, in the next lecture, about hardenability of metals.